quickly complete our discussion of Kaluza-Klein compactification just in particle. Okay. We discussed last time what happens to the square root g e to the power minus pi square root g Lagrange. Okay. What we did not discuss is what happens to the other part of the action, which is, there's this two-form B field. How do we know there's this two-form B field in string theory? We know that because there's a vertex operator for this. What was the vertex operator for the closed string? There was del x mu, del bar x mu. These x mu's had to be transversed to k's. Any shift of the polarizations with k was trivial, but other than that, there was no restriction. Okay? This thing in mu could have been traceful, traceless, symmetric, and asymmetric. So we can decompose these mu structures into symmetric structures. So there's a traceless symmetric part, a trace part, and an antisymmetric part. Okay? And the traceless symmetric part was what we call the dilaton. Sorry, the traceless symmetric part was the graviton. The trace part was the dilaton. The antisymmetric part is what we call p. Okay, now, just like the null state for the graviton, the fact that if you take epsilon and you shift epsilon by something proportional to k, okay, that doesn't change the amplitude. That is associated with the gauge invariance, which is for the linearized graviton h mu goes to h mu. In the same way, the null state for this B field, for this antisymmetric part, is associated with the linearized gauge invariance B mu goes to B mu plus D mu theta mu minus D mu theta. Okay, just the same algebra that would use the first, would give the second, just replace its symmetric values. Okay? But you see this guy was antisymmetric and can be written in the language of forms. This is B goes to B plus B zeta. Okay? So string theory comes along with, apart from a graviton and a scalar field, this dilaton, the interpretation of the coupling constants, we'll see it more and more as we go. Of course, it comes with an antisymmetric field. Okay? It comes with an antisymmetric field. Now, this antisymmetric field has a gauge invariance that is a natural generalization of Maxwell gauge invariance. Instead of A goes to A plus D of function, this is B goes to B, which is a two form, goes to B plus D of one form. Okay? And you can ask, what is the natural space-time effective action for such a field? Well, the natural space-time effective action is all, as usual, is written in terms of the field strength. So what's the field strength? Field strength should be something that is gauge invariant. It's dB. The dB which was called H. So the natural space-time effective action is H mu rho K. Okay? So, string theory in 26 dimensions has such a term. Actually, this whole thing will be h mu rho raised, of course, by the metric. There will be square root g and the minus. There will be such a term in the space-time effective action of string theory in 26 dimensions. Okay? You could confirm this, for instance, by computing scattering amplitudes between two B particles and two gravitons. Such a scattering amplitude would have a vertex from such a Lagrange, because it's a B particle, and then various gravitons either in the upper G value that is used to contrast indices or in square root G. Okay, so such a scattering amplitude would be non-zero if it predicts what it is from this term at lowest order. And lowest order. This is just the lowest order effective action of the higher derivative terms. Okay, and you could check that just in the way that when we computed graviton scattering, we claimed to be never in detail that you go to low enough energies and you can reproduce it from the Einstein differential. In the same way, graviton, BB scattering at lowest in the low energy limit will be reproduced from such a differential. It's one way of checking for such a term actually. Another way Pranjal will tell us about in his lecture on Thursday. Okay. Just to preview that, Pranjal will explain that there is another coupling you can add to the string, which is B mu del x mu del y mu epsilon alpha epsilon. This term, when B is constant, when it's zero, of course, it's not there. When it's constant, is a total derivative of the y sheet of the string, and so it's effectively not there. Now, can somebody see why this is total derivative when B is constant?
Because delta alpha beta acting on 1x will be 0 because of the symmetry.
Exactly. So you can just pull one of these deltas out. Because it doesn't act on B because it's constant. It doesn't act on this guy because the symmetry of this derivative is killed by the antisymmetry of that epsilon. And then it's just total derivative. In fact, more generally, that argument tells you that, you see, if some structure involving the derivative of this B is 0, okay? So let's see that more generally. Suppose I put this del alpha. So I get a del alpha of B mu nu x mu del bar x mu beta. And if B is not a constant, I will in addition have plus del alpha B mu nu x mu del bar x mu epsilon alpha beta. Okay? When B is a constant, this is 0. But more generally, if B is not a constant, what is this? Well, we can use the chain rule. Okay? We can use the chain rule to get del x rho, del alpha x rho, times del rho B mu nu.
What is that?
Okay. This B depends on x. B is a function of sigmas because it depends on x. So I'm using the chain rule. What is del alpha of B mu nu? It is del rho of B mu nu times del alpha of x. Okay? Then there's this x mu, there's this del alpha, del bar, okay, del alpha, del beta, x mu, and epsilon alpha beta. Okay? Now, you see, this rho index and this nu index here occur with del alpha x rho and del beta x nu. So rho and nu here occur with a structure that is effectively antisymmetric because of the epsilon alpha beta. Do you see that?
Right.
So this derivative, though it's not immediately apparent, is actually a completely antisymmetric derivative of B. Okay? So more generally, provided this antisymmetric derivative of B vanishes, this thing is a total derivative. But that's the same thing as if H vanishes. Okay? So if we're in a space where H is 0, putting this B here on the worldsheet of the string does nothing. But when H is not 0, it does something. It changes the worldsheet of the string. And Pranjal will show us next class that it changes the beta function equation for the velocity of the string precisely in such a way so that the beta function equations can be reproduced from an effective action of this form. Okay, now I want to very quickly, just the point of the next 5 minutes is to try to understand how this guy reduces under Kaluza-Klein reduction.
That is same as in B the closed form.
Correct. So that if B is that's right. If B is 0, then it's trivial, apart from global things. Right. So, you see, what is B? So, B was two forms that had the form dx mu, dx mu. B, let's call it Bmn, dxm, dx. Now, under our Kaluza-Klein reduction, this n index range number.
What is it?
I'm writing the two form in two form language. Okay. Now this n runs over all indices. xd, the circle direction. Okay, so let's say that this m index is mu and d. Okay. So once we do our circle reduction, this Bmn, so two types of fields in Bmn. There's B mu nu. So Bmn, so B is equal to B mu nu dx mu dx mu plus two B, let's say d mu dx d dx mu. Two because there are two such terms. What?
Isn't it antisymmetric if two such terms add up?
What? Two such terms add up because B d mu will be minus B mu d. So what will you get? You get B d mu dx d dx mu plus B mu d dx mu dx d. Now this is minus this and this is minus this.
Because that is a wedge product.
Because it's a wedge product. Sorry. Everywhere it's a wedge product. Okay? So what you see, and this is sort of obvious, is that a two form in the parent space-time without the central dot magnification reduces a two form and a one form. Okay? So if we do Kaluza-Klein reduction in a theory with a two form, the daughter theory is going to have a two form but also a one form. Okay? Let's see how this works at the level of gauge invariance. Okay? At the level of gauge invariance, what we said was that we had B went to B plus D in. Okay? Now our A itself had components of the D direction or the mu direction. So A was, let's say, some lambda tilde dx d plus A tilde mu dx mu. So now let's decompose this. Okay? So if we had our B, which had this decomposition, okay? So we have B mu nu dx mu plus 2B d mu dx d dx mu goes to B plus dA. So now we just take this and plug in. So what do we get from here? Everything here, by the way, is functions only of x using the Kaluza-Klein logic. Okay? So what we get from here is plus d lambda tilde L mu lambda tilde dx mu dx d. Yeah. Plus del mu A mu tilde dx mu dx mu. Is this clear? So the shift in the daughter B is exactly the same form as as it was in the parent. B tilde, B daughter, goes to B daughter plus D A daughter. Okay? On the other hand, this B D mu goes to up to a normalization. You'll have to renormalize this lambda by a half or a 2 or something like that. Yes, just picks up a standard gauge transformation, a standard zero form gauge transformation, Maxwell gauge transformation with this lambda. Okay? So you see that it's correct that this 2 form goes to a 2 form plus a 1 form, under which the gauge transformation of the original 2 form becomes the gauge transformation of the daughter 2 form plus the gauge transformation of the daughter 1, daughter Maxwell.
How is it a 1 form? It's DXD, DXD, right?
No, it's a 1 form because, we don't count DXD as, we're only looking at structures at the base on X mu. So DXD is not counted. You see, it's a 1 form under rotational transformations in the X mu space. XD is chosen as special.
Lambda tildes don't depend on the.
Let's say it again. Do you remember what our diffeomorphism transformations were? You see, we had diffeomorphisms in the parent space. Only a subclass of diffeomorphisms survived Kaluza-Klein reduction.
Yeah.
What were they? Diffeomorphisms of the lower dimensional space and the Kaluza-Klein gauge fields, gauge transformation. It's a 1 form under the diffeomorphisms of the first kind, diffeomorphisms of the daughter fields.
And you say the 1 form is under DXD in the other one.
That's right. The fact that there is some DXD going on will now tell you that these things are not gauge invariant under the Kaluza-Klein gauge transformations.
Yeah.
Let's examine that immediately. Okay? So suppose we had BMN. I now want to see how BMN. Okay, so BMN, which we decomposed as B mu nu dx mu dx nu plus with some normalization. I'll just call this a tilde mu dx d dx. This new gauge field. Now I want to see how this transforms under the gauge transformation of the Kaluza-Klein gauge transformation. Here, let's remember what the Kaluza-Klein gauge transformation is. The Kaluza-Klein gauge transformation was that XB was XD plus lambda of XB. So I want to see what the transformation of this guy is. Now, because there's no XD anywhere here, this tells us that B mu nu itself is gauge invariant. But because there is an XD here, okay, that tells us that A mu tilde is not gauge invariant. Let's figure out its gauge transformation property. Sorry, I even said it wrong. Sorry. Let's figure it out, and I said those words wrong. In fact, you'll see. Because dx mu will go to a dxd will go to a dx mu. So that tells us that this is gauge invariant, but this is not. Exactly. Let's see. Let's look at what this transforms, how this transforms under Kaluza-Klein gauge field. Gauge transformation goes to B mu nu dx mu plus A mu tilde dxd dx mu plus what we get from the change of dxd. Change of dxd is what? Gives us plus del mu of lambda dx mu times A mu tilde dx mu dx mu. Alright? So what's that? So this part, the dxd dx mu part is invariant. So what we get is that A mu tilde invariant. Okay? A mu tilde is invariant, but what about B mu? It's not invariant. In fact, B mu goes to B mu plus A mu tilde wedge D nu lambda. You know what I mean, right? Antisymmetrize A nu lambda. Extensive wedge. Say antisymmetrize. You can say components. You know what I mean. That's a fancy way of saying it. B goes to B plus A wedge. That's the right way of saying it. Now, this is sort of interesting. This is sort of interesting because DB, therefore, okay, DB, let's look at the gauge transformation of DB.
And to be clear, when you write A as a one form, it's just A mu dx, not A mu dx dx.
Exactly. That's an intelligence. Now, yes. Now everything is in the Doctor space. Yes. Okay. So, dB, how does that transform? So we have dB goes to dB. D squared is 0. So we get a contribution purely from here. Plus dA tilde. So it's field strength. Wedge D lambda. Okay, so what we say is that, look, dB, which is some nice object constructed to be gauge invariant under the one form gauge invariance. And in the parent space, it was fine, right? You wrote down H mu nu, H mu nu, H mu nu rho, H mu nu rho, you got a nice gauge. But in daughter space, if you try to write down H mu nu rho, H mu nu rho, this object will while gauge invariant under the one form gauge invariance, will not be gauge invariant under Kaluza-Klein gauge invariance. Because under Kaluza-Klein gauge invariance, it's transformed. Okay? So how do you think one can deal with it? How do you think one could deal with this? Well, one way of dealing with this is the following. Suppose we define H hat.
So isn't the whole procedure much clearer if you replace d of xd as d of some xd plus a mu dx mu?
D of xd?
D of xd plus some mu, some a mu dx mu. Because basically in G mu nu the gauge transformation is basically if you Kaluza-Klein reduce there will be a gauge field and effectively
No, we have that. We have that in the metric. So
the effective forms that you are writing in the compact direction, they basically are some dxd plus some gauge field into x, some one form.
from one form. So in the metric we were careful to write dx. How did we do it? dxd. How did we do it? Dx
a mu
plus a mu dx. Yeah, we have dxd plus a mu dx mu the whole thing. So in the metric, this was nice.
Block gauge.
Exactly.
This will basically ensure gauge transformation.
This ensures the gauge invariance. Exactly. So as you say, basically what we need to do is to, and the metric explicitly did that. Okay? But here now, I want to say what will, so you're saying just always replacing this by this structure? That might actually that might be good. Okay, but let me just proceed algebraically at this point. So we've got this object here, okay, and I want something that will be gauge invariant instead. So how do you do it? Well, suppose I take dB minus A times dA. You're probably right.
This will automatically come out to be this.
Yes, I suppose. Yes. But suppose I just took this structure. Yeah. dB minus A d tilde. Then under gauge transformation, you know how dB transforms. It transforms with a dA tilde plus d lambda. We also know how this transforms. This transforms with d lambda. This transforms with a dA tilde. I mean, this is dA tilde. A tilde itself was gauge invariant under Kaluza line. So this combination here is a gauge invariant. It's gauge invariant automatically under one form gauge transformations, but it's also gauge invariant under Kaluza line gauge transformations. Okay, so what we might guess is that if we do the Kaluza-Klein reduction of H mu nu rho, sorry, H mn rho, H mnp, H mnp, we do the Kaluza-Klein reduction of H mnp instead of predicting that we would get H mu nu rho, we should expect to get this combination mu nu rho. So let's give this guy a name. I think some people call it, I'll call it H tilde mu nu rho. We should expect to get H tilde mu nu rho, meaning H tilde mu nu rho. Okay? Now let's actually just check in 2 minutes that this is what we actually get. Okay, so what this was in the higher dimension was clear. Since this is a nice gauge invariant combination, this is what you might expect to get one dimensional reduction. And I'm going to check that we actually get it.
You did the transformers?
Yes. This is the Church. This set DP. It's the Church answer. So yeah, this is, so for those of you who are familiar with this is a very simple explanation for where you get Church answer. You start with a Lagrangian that is simple in 10 dimensions. In order for it to respect all gauge invariances in the lower dimension, you need these mixed field strengths. These field strengths that are not just dB but mixing with other things. And that's where is one source of Chern-Simons disturbance in certain dimensions. Okay? So, just to complete our understanding of this, let us confirm that we actually get this structure. Just from algebra. Okay? So in order to do that, let us quickly remember, if somebody can, we worked out the inverse metric. We worked out the inverse metric in class last time. Somebody can reproduce that for me. What was G, DD, G, D mu, and G mu? We could work it out again if it's hard to find. Shall we work it out again? Yeah, give it. G mu nu.
Is G mu nu up again? Reduce.
Okay, so let me first remind you what the metric was. So the metric was ds squared, which is equal to d mu nu, dx mu, plus e g d d dx d plus a mu dx mu everything squared. So the metric of lower indices was gdd was gdd gd mu came entirely from here, so that was equal to gdd a mu and g mu nu was equal to g d was g mu nu plus g d d a mu a. Okay, and then we worked out the inverse metric. So the inverse metric, if I'm, are you saying this was just g mu nu?
Yeah, G mu nu out.
Okay, and what about?
This is a dot g minus a dot g.
G mu nu
A mu. Is this right?
Yes.
Minus.
minus G mu nu A mu.
And then A dot G dot A. A mu G mu A mu. Plus 1 by G.
Plus 1 by G. Plus 1 by G. Right.
Another minus is offset to the
And yeah.
Excellent. So, now what do we have? We have H M N rho, M N P, H M N P, okay, G M M prime G P P prime G N N prime. That is the objective what it gives. Now, what are the possibilities? One possibility is that all indices here are the mu and nu indices. In that case, we will just get contraction through G mu nu. Okay? So that will be the path that is dB times dB contract. Then there's another possibility, which is one of these indices is a D index, but these indices are all mu indices. Okay? Suppose one of these indices, let's say the P index, was D. Then we would get G P P prime. So P was D, but P prime was a mu index. So we're looking at the case where these guys are mu indices, and this guy was a D index. Okay? So we would get one factor of this object. Okay? So we would get one term with one A mu here. So this object would be H M N. So a mu nu and a D. So that's what we had earlier called an F tilde. Because F tilde was the field strength of the lower dimensional gauge field, and its field strength is H mu nu D. Okay? And then from here, from this G, we get the A. Okay? So you see the structure coming, right? The F tilde, A, and H mu nu. We get two such terms, so those are the cross terms, the two cross terms in this H tilde square. And then finally there are the terms in which both terms, in both of these you have one D index. Okay? Now, that structure has two possibilities. Either you could use the D index contracted with the D index. In which case, what would you get? You'd get field strength square. Do you see? If you have the D index contracted with the D index, you'll get field strength square from this piece. Okay, plus some A stuff. Okay, and the other possibility is that you have D index contracted to the mu index. In that case, and the other D index contracted with the mu index, that case again you get two A things. Okay, both would have field strength square. So you see the structure is that you get your field strength F tilde square. That came from both D indices being contracted through this and using this term in the inverse metric. So just a Maxwell term for the lower dimensional Maxwell field strength. That will come from here. All the other terms involving quadratic in A will group together to give you what you need for your gauge invariant H tilde square. Okay, I have tried to work out the numbers for you. But you see that all terms are there, and all of the right structure. And I'll leave it as an exercise for you to check that it all works out. Okay? So, of course this had to work, because you started with something gauge invariant in your parent theory. You're bound to get something gauge invariant in your daughter theory. And we basically figured out just by trial and error the unique gauge invariant structure for these kinds of criteria. Okay? So, what was the next? Let me just end this with a summary. The summary is what? The summary is, I'll just write down now with all factors and so on, that if you start with square root g e to the power minus 2 phi h m n p h m n p, and you can reduce this, you will get something proportional to some numbers, then square root g. Okay, then e to the power minus 2 phi d. This phi d differs from this phi in exactly the way that we saw last time. This just absorbs up some effective factors of this GDD. Right? So this phi d differs from this phi as phi d is equal to phi minus sigma by 2, where dB was equal to sigma.
So you're writing it in Einstein base, right?
No, because I've got an overall limit or something. Hang on, let me finish the answer. Einstein frame. No. Writing it with the lower dimensional limit on as well.
This G is big G. This root G.
This root G is big G. This is some small g. It's not Einstein's frame. It's some string, some analog of a string frame in the lower dimension. If it was Einstein, this term would be there. Okay? And yeah. You get h hat mu rho, h hat mu rho plus e to the power minus plus 3 e to the power minus 2 sigma h d mu h d mu. This is the Maxwell term for the field strength. This is the f hat square, and this guy is the gauge invariance dB plus a times f whole thing square. Okay. You can ask, why is this e to the power minus 2 sigma there? That's just keeping track of the factors of 1 over t. You know, the fact that this is there because there are this expression is not homogeneous in these GDs basically. So that will give you a relative e to the power minus sigma.
What is the
This
after 3 e to the minus 2 sigma?
h d mu h d mu. This is what the same thing that we call f hat mu f hat. It's the field strength for the one form. This is a Maxwell term for the one form gauge field, and this stuff is dB whole square plus the Chern-Simons terms added in a way to make it gauge invariant under also Coulombic. Okay? The point of presenting this was just to show you how something that is very simple in 10 dimensions or in 26 dimensions under Kaluza-Klein reduction can rapidly become quite complicated. You know, where this field strength, involving these mixed field strengths, 8 mu rho, remember dB, h was 8 hat was dB minus a f hat, and so on. Okay, but this complexity had a very simple origin. We'll see the same when we look at the more realistic supergravity actions, or the more elegant supergravity actions. Those are type 2b theory, for instance, or type 2a theory. Actually, when we look at type 2a theory, we'll see exactly this structure. This type 2a theory is exactly obtained by dimensional reduction from 11 dimensions supergravity. We'll see exactly this kind of Kaluza-Klein structure. Sorry, Chern-Simon structure. Okay, that's all I want to say about this Kaluza-Klein story, just without strings, just in just field theory, just particle theory. Any questions or comments about this? Okay? Sure. Okay. So, if we had just the zero modes, just particles propagating on circles, already we see the things that you get, things that are quite nice. New structures emerging at long distances that weren't put in the old structure. Let's review what they were. The first thing was that if you had just diffeomorphisms in the whole space, and then you restricted to configurations that preserved an isometry in the circle direction, the diffeomorphisms of the big space reduced to diffeomorphisms of the small space plus gauge transformation of the small space. Correspondingly, the graviton of the big space reduced to a graviton of the small space plus a gauge field of the small space plus a scalar field. What was the scalar field? What is the physical interpreted scalar field? What physically, geometrically, what was it in the big space? GD. The size of the circle. There are circle compactification. Every geometry is dynamic in general, and the circle on the average can be fixed, but its size can fluctuate. The size of that circle was the scalar. What? Let's not use, in string theory, in addition to the size of that circle, we had an instrument. Let's not use words. It's the size of the circle. That's the additional theory. Yeah. What you call the Newtonian often gets, so often a lot of terminology. That's, yeah. Okay. Moreover, if you start with a two-form field strength in the high dimension, that went to, two-form potential in the high dimension, that went to a two-form potential plus a one-form potential in the low dimension. And in the high dimension, the Lagrangian was just d2 form square. Low dimension is more or less d2 form square, but with mixings. So as to ensure Kaluza-Klein gauge invariance. Okay. Any questions or comments?
So far, this is just Toda's compensation, right?
Circle, not even Toda's.
Yeah, circle. So if I do it on spheres and etc., you get array structures.
You get more interesting things.
Nice.
Already at the level of particle physics. And the most striking thing that you get is the following. Now, we briefly discussed this last time, but let me say it again. You see, suppose you've got a compactification manifold which has an isometry. Yeah. Every isometry gives rise to a gauge field downstairs. This was the special case of the isometry being translations along the circle. Okay? And the gauge transformation you saw was just taking that translation along the circle and making it x mu dependent. Because xd goes to xd plus f of xd. Okay? In a similar way, if you've got an arbitrary isometry on your compactification manifold, that will give rise to a gauge field. But the isometry group need not be abelian. For instance, on a sphere, the isometry group will be an SO. Okay? So you can easily get non-abelian gauge fields and non-abelian field strengths through Kaluza-Klein reduction on more interesting than flat spaces like
Potential will have some scalar structure will be there.
Yeah, so you'll have scalar structure depending on deformations of this compactification manifold. But in addition to that, you will have new vector fields. And I emphasize that the vector fields are associated with isometries and need not be limited by the dimensionality of the compactification. In this particular case, we compactified one dimension and got one vector field. But if we compactify two dimensions on a torus, we would get two vector fields. Very similar. But if we compactify two dimensions on a circle, on a sphere, because you have to have equations of motion, you have to field content that allows you to have a sphere. The sphere would be, spheres tend to shrink in general. You have to be supported by something, some flux or something like that. Okay, so you can't just do whatever you want. There has to be a solution of the theory. Circle compactifications, you can do what you want. It's just an identification of flat space. It's a solution of the classification. Sphere, that's not in general, it's not a solution. You can't just do whatever you want. It has to be a solution. But once you've got a solution, if you manage to find a sphere solution in your problem, where one in your internal dimension is a sphere, you will get 3 gauge fields, even though you're compactifying only 2 dimensions. Because the associated isometry group is SO3. It's 3 generators. Okay? So you can get new gauge fields, and the amount you get is not it's not directly tied to, it's not equal to the number of dimensions you compactify. You can get more. You can get less. You can compactify on a manifold with no isometry, no gauge fields. Okay, so it's a rich structure. Some of which we will see as we go.
Isometry will fix you some constraint around the gauge fields. Like say you take SO3, there will be 3 gauge fields. So there will be a constraint followed by this gauge fields. Like
there will be commutation
relation
among these gauge fields. There will be they will have
effectively
two.
2.
What?
Effectively there will be 2 gauge.
No. There are 3 gauge fields.
They will satisfy the SO3 algebra.
But that doesn't mean there's a constraint.
So why I ask this is because generally you do Calabi-Yau compactification in which you have no isometries, so to say. And generally I'm on the other end, the torus compactification. Is there any phenomenologically inclined model in between where people do compactification in non-trivial manifolds?
Oh, this was a big game in the 1980s.
So there was a game.
It was a big game. You see, before string theory, the idea was to try to generate realistic models of particle physics from supergravity.
So this extra dimension.
The supergravity people tried to generate realistic models of particles. People who are doing supergravity, of course, were motivated to connect it to the real world. Okay, they tried to generate realistic models of particle physics from supergravity. And the main problem they had was it was very hard to get chiral matter. You see, because you see the point, right? Even if you start with a chiral theory,
both you lower dimension you will get both
ways. That was the main stumbling block of it. People tried 11-dimensional supergravity, putting it on S7, putting it on all kinds of things.
And this is what Calabi-Yau basically fixed.
In the heterotic theory on a Calabi-Yau allowed you to get chiral matter very easily. That was the big. Yes. It didn't work very well precisely because of the difficulty in getting chiral matter. There were even theorems about how large a gauge group you can generate, starting from 11 dimensions. I've forgotten the theorem. The rank cannot be larger than such and such. You cannot have such and such. People were trying to get grand unified models doing this, and it didn't quite work. Okay, yeah. So good question. Worth trying. Okay. Other questions about it?
You generated Chern-Simons like gamma in any dimension.
Yes, it's not a 3-dimensional. Is that what the question is?
It has to be odd dimension for Chern-Simons to exist.
Well, by Chern-Simons, I just mean that we've got a gauge field rather than a field strength. Okay? So this is not the most, it's not an A wedge, F wedge. You see, there are lower index terms and upper index terms. So this is not a structure without a matrix. Like I said, this is not written entirely in terms of wedge products. So let's expand out this guy. This was A wedge F wedge star of H to the lambda. Let's say. So there's this star, and the star knows about the metric and so on. It's not Chern-Simons, that's it. At Chern-Simons, all I meant was terms that involve gauge field, not fixed field. That's all I meant by Chern-Simons. Terms that do not manifest in terms of field fields. That's all. Okay. Right. Now we want to move on to string theory. String theory and so on. Okay. In order to do that, let us very briefly recall our quantization of the string. Okay, let's take the direction that's going to be a circle. We have 1 over 4 pi, right? Del x, del x, del x. This was our world sheet action for the string. And you remember that the only thing I want you to recall is that we got oscillators plus 0 modes. Okay? And I'll remind you of the structure of the 0 modes. The 0 mode structure was that the 0 mode structure was that x mu x was equal to x naught plus p tau times the number. Okay, x was equal to x naught plus p tau times the number, and this number was fixed by various considerations, but basically by canonical quantization. So let's recall how we fix that number. Moving to the 0 mode so that we do the integral over sigma, we have 1 over 2 alpha prime x dot square. So canonical quantization tells us that x dot by alpha prime is equal to p. So this is an alpha prime. What? Root 2. No. Let's look at this. We have 1 over 2 alpha prime. Just canonically quantize the derivative of the Lagrangian with respect to x dot. That's x dot by alpha prime. That's the canonical point. So P is x dot by alpha prime by x dot is P times alpha prime. There was some root 2 in the relation between alpha 0. Forget about that. Okay, so this was a 0 mode structure on the world sheet of the string. Okay, and you notice that the 0 mode structure has the following property. Of course, with respect to the fact that x of sigma was equal to x of sigma plus 2 pi, just because we had a closed string. Sigma and sigma plus 2 pi were the same point, so the fields had to be the same points. But now, suppose x is circle valued. Okay? Suppose x is circle valued so that in space time, x is the same thing. X is the same thing as x plus 2 pi. Okay? In such a space-time, the most general configuration of a string, again, the most general configuration of a string in sigma need not be such that x of sigma plus 2 pi is x of sigma. In fact, you could have more generally that x of sigma plus 2 pi is equal to x of sigma plus 2 pi n times r. Let's go down. W times r, where w is any integer. This is an allowed configuration of the string. Physically, what is it? It's a string that winds around the circle. W times. Is this clear? As you go from 0 to 2 pi, that's from one end of the loop, you go around the loop. As you go around the string loop, you wind around the space-time circle W times. Okay. Now it's clear that if you have only closed strings in your theory, sectors of configuration space, okay, with different values of W are distinct and cannot by small fluctuations talk to each other. This is clear? Right? Because without breaking the string, you cannot change the winding number. And if you have only closed strings, strings never break. It's more interesting when you also have open strings, because then those strings can break. And we'll discuss this very soon. But at the moment, let's look at the theory of the omega.
What are statements? Different omega corresponds to what?
Different sectors, such that if you get different sectors of the Hilbert space. Hilbert space will be labeled by omega. Fluctuations around any configuration. You'll have to quantize the theory omega by omega. The classical phase space of the theory splits up into disconnected sectors labeled by omega. And therefore, Hilbert space splits up into disconnected sectors labeled by omega. This is clear, right? So, now what we have is something interesting. Okay? Now what we have is something interesting. What we have is we have more to Hilbert space. Hilbert space of this string is labeled by winding sectors. But we also have a restriction compared to what we have. What is the restriction? The restriction is that the momentum conjugate to x, this x dot, is now quantized. Why is the momentum quantized? It's because in the zero mode sector, the wave function was e to the power I p x. And since x and x plus 2 pi r were the same point, and since we wanted the wave function to be single valued, now this is the space-time wave function. Yeah, the wave function as a function of this zero mode in space-time. Right? I'm sorry, it's the wave function, right, as a function of the zero mode in space-time. Since x and x plus 2 pi r are the same thing, we must have that p times 2 pi r is equal to 2 pi times an integer. And therefore p was equal to integer divided by r. It's the wave function of zero. Let's remember how we quantize the string. The string broke up into a bunch of harmonic oscillators plus a Lagrangian for the zero mode. The zero mode Lagrangian was just this. So we got the Hilbert space was that of non-relativistic quantum mechanics. The wave functions of the zero mode were the eigenfunctions were labeled by momentum. Those were the eigenwave functions. But they had to be well defined. They're the same wave function on points that are identified with each other. The usual story.
Basically, initially we had a free propagation string which can vary any momentum.
Yeah.
But now because of this compact.
Because the circle is quantized, the momentum is discretized in units of 1 over r. The usual story. Okay? So we have both something new winding sectors, as well as a restriction of what we had before. Instead of allowing all momenta, we have only particular momenta. And now, instead of having instead of having x of sigma plus 2 pi, we have x of sigma plus 2 pi. Not x of sigma as before, but x of sigma plus a whole lot of options. Okay. So now, let us now look at the. So now we've got to re-quantize the string. We've got to re-quantize the string in each omega background. Okay? And you might think, okay, now we've got a huge job ahead of us. But actually, this huge job is very simple. Because as we will see in a minute, the oscillators don't change at all because of the winding sectors. So let's see how that goes. You see, suppose we want to sit in winding sector time. Okay? What I'm going to do is to have x is equal to some configuration that has winding number w plus x tilde, which will then expand into an arbitrary Fourier expansion for a single valued gauge field, a single valued x field. Because we've already got the winding that we want. Let me say this here. Suppose I choose some particular configuration such that of sigma this is a particular configuration such that x tilde of sigma plus 2 pi is equal to x tilde of sigma plus 2 pi n w r. Then for this whole x to obey the correct periodicity, this guy will just have to have the ordinary periodicity, because this is already coming from here. Is this clear? You see, the thing that you pick up as you go around is just an additive part. So if one piece has that additive part, the other piece has to have nothing. Okay? So we can work in a winding sector W by using this trick. By first looking at a convenient guy and then an arbitrary fluctuation of that. Now what is the convenient guy? Okay? You see, the convenient guy is something that solves the equations of motion of the Lagrangian. Because then the Lagrangian will be completely quadratic in terms of the fluctuating points, x double t. So let's find a solution to the equations of motion of the Lagrangian that has winding number W. But you see, what was the equation of motion for the Lagrangian? It was del squared x is equal to 0. So it's very easy to find a solution that has winding number W. Because any function that's linear in sigma solves the Lagrangian, solves the equation of motion. Because del squared kills any linear function. We didn't have this linear function in sigma before, although it solved the equation of motion because it didn't obey our periodic boundary conditions. But now, in fact, we have to have such a thing because we need it to obey the boundary conditions. Okay? So, what is the convenient choice to make for x tilde? It's very clear. X tilde. So now I'm going to stop writing such complicated notation. X is equal to, I'll just write what we need. What we need is just W sigma R plus the fluctuation. Right? So sigma goes to sigma plus 2 pi, x goes to x plus 2 pi r delta. Simple. Okay. Now we just plug this into the Lagrangian. We just plug this into the Lagrangian and find the effective Lagrangian of all this x tilde. Okay? Because this guy is a solution to the equations of motion, there's no term linear in x tilde with this guy. So you get whatever you get from here plus quadratic in x tilde. Quadratic in x tilde is just the same action but for x tilde. And then whatever you get from here is what this evaluates to the action. So what does this evaluate to the action? Let's compute that. Okay, we get 1 by 4 pi alpha prime. 1 by 4 pi alpha prime times so del sigma x the whole thing squared basically, right? Okay, times of course beta. Okay, so del sigma x is omega r, so omega squared r squared, integral over sigma gives 2 pi, so that's 2 alpha prime, and then there's an integral beta. Okay, now if we were doing the Lorentzian theory, we should be a bit careful about signs. The Lorentzian theory is equals x dot squared minus x prime squared. Okay, so this would come with a minus. I'm assuming x is one of the space-like directions.
Yeah, but what about the cross term?
The cross term would be 0. The cross term would be 0 basically because this solves the equations of motion.
Oh, everything else is figured out.
Exactly.
Okay.
Exactly. Okay, so we get this with a minus sign. Now, you know the Lagrangian is kinetic minus potential energy. Okay, so this thing is just a minus of the potential energy. Came from the x prime square. So this thing just gives you a contribution to the energy of your state. What is the contribution? It's omega squared r squared by 2 alpha prime. Is this clear? So the L0 plus L0 bar of your state with binding number W as an additional contribution to what you got before, and that additional contribution was omega squared R squared by 2. We'll use that in a moment. Okay. So now let us recall the mode expansion of the string. As we said, we have this x tilde is equal to x naught, which we ignore. Okay, it's needed, but okay. Plus p alpha prime tau. And you recall that this p was quantized in units of n by r. So n by r. But in addition, we have plus W sigma r and plus oscillators. Oscillators are entirely unaffected, as we've seen, because the Lagrangian for x tilde is the same as the Lagrangian for x. X tilde was not entirely unaffected completely because the zero mode was periodic. Okay? But the oscillators are just entirely unaffected. So the oscillator expansion is untouched by this toroidal expansion. So whatever we did previously continues. I'm not even going to talk about that. Okay? The zero mode expansion though, which previously, let's compare this to x tilde was equal to p sigma, alpha prime p sigma, has been replaced by this. Let's ignore the x0, it plays no role. It's there in both sides. Okay? Now, you may remember that what we did last time was break this up into left moving and a right moving part. Like this was done. We broke this up into left moving and right moving. We call this alpha prime p by 2 tau plus sigma plus alpha prime p by 2 tau minus sigma. And then when we when we broke up x into a left mover and a right mover, this we grouped with the left mover, and this we grouped with the right mover. Because this was right mover and that was left. Let's do the same thing with this mode expansion. Okay? So now how will we do it? So x tilde is equal to what do we see? X tilde is equal to now let's write this. So what I'll do is replace tau as equal to tau plus sigma by 2 minus plus tau minus sigma by 2. And similarly I'll replace sigma is tau plus sigma by 2 minus tau minus sigma by 2. Okay? So let's look at the coefficients of tau plus sigma. We will get, let's say by 2, we will get n alpha prime by r plus omega and n alpha prime by r minus omega tau minus sigma. Okay. It's traditional to write this, the coefficient of tau plus sigma by 2 following here, as alpha prime p left. So previously we had p left was equal to pr was equal to p by 2. And then you can write the mode expansion as alpha prime p left by 2 tau plus sigma plus alpha prime p right by 2 into tau minus.
You are using an R here, so it has omega R here.
Omega.
N by R plus omega R.
Yeah,
You should have this duality R going to 1 1.
Thank you. Where did I first miss that R? I had it here. Thank you. Yes. Okay. formula P left is equal to N by R minus, it's a plus omega R by alpha. And P right is equal to N by R minus omega R by alpha. Okay, is this clear? Now, L0 plus L0 bar, the Hamiltonian. L0 plus L0 bar, the Hamiltonian of our theory, used to be what? It used to be the number operator, the harmonic oscillator Hamiltonian, plus what came from the 0 volts. Let's quickly remember what it was. That was x dot squared by 2 alpha prime, and then this is, so p squared by 2n by n is 1 over alpha prime, so alpha prime by 2 p squared. So it used to be alpha prime by 2 p squared, or it used to be L0 was alpha prime by 4 p squared, and L0 bar was also alpha prime by 4 p squared from the contribution from the 0. Okay, that's how we had it without these cellular identifications. Okay, this is alpha prime PL squared, no, PL was what? P by 2, correct. So alpha prime PL squared, so L0 was alpha prime PL squared, L0 bar is equal to alpha prime PR squared. The full energy will continue to be PL squared plus PR squared. We have a physical interpretation in a moment.
Continue to it using a comment that W squared R squared is the connection energy.
What? Yeah, you can. It's use the same ones. Yeah, of course. Yeah. So what Ronak's comment was is that we continue to get alpha prime p squared by 4, so that is, which now will be replaced by n squared by r squared. But then you also get the potential energy which we worked out. And though we worked it out, I can't remember. Omega squared r squared, somebody help me. W squared r squared by 2 alpha prime.
Yeah.
And this is p squared by 2. Sorry. Because you have that. So Ronak's comment was that the full energy, fine, let's do this, is p squared, kinetic energy, potential energy. Okay? Easy to check that this is the same as alpha prime PR squared plus alpha prime PL squared. Just cross terms cancel. Okay? Yeah, so easy to check that you get this. And there's something interesting about this. So let's look at this formula. Let's write it a little nicer. N squared by 2 R squared plus omega squared R squared by 2. So what we have here is a set of energies, one for each pair of integers n and m. Now you can ask the following question. You can ask the following question. Look, are there, as we change R from 0 to infinity, does this set of energies change? Or do you get the same set of energies, collection of energies, at two different values of R? And all of you know the answer to this question. It is that if R prime is equal to 1 by R, or alpha prime, you get the same collection of energies. Square root
Square root alpha beta.
Square root alpha beta.
There is an alpha prime by r square.
No, just dimensionally, this is length. This is length, should be r square.
Sorry.
Yes. Okay.
Self radius.
That's right. Yes. So if r prime is alpha prime by r, you get the same collection of energies. Why? See, so let me write this now in terms of r prime. Okay. This will become n squared r prime squared by 2 alpha prime plus this becomes omega squared alpha prime by 2 r prime squared. And you see, this gives you the same. You see, this formula with r replaced by r prime. If you also replace n and w. So what we are saying is that a circle of size r and a circle of size alpha prime of radius r and a circle of radius alpha prime divided by r has the same spectrum of the Hamiltonian, except the labels get interchanged. A state with momentum n units of momentum and w units of winding in the first circle has the same energy as a state with w units of momentum and n units of winding of the second circle. Is this clear? This observation, which we're soon going to formalize into a more serious observation, okay, is the observation that we're soon going to formalize this into the following statement. That these two conformal field theories, you take a conformal field theory with a circle of size r, and another conformal field theory with a circle of size alpha prime by r. They look different, but actually, at the level of conformal field theory, they're the same conformal.
This statement that the spectrum is the same.
So far, I'm going to explain how it is.
This is some bullshit.
What?
Is this the
This is T duality. Okay, this is our first run-in into this statement. As you say, so far we've only seen that the spectrum is the same. Okay. Yeah. Now we're going to try to see more seriously that these two things are the same. The first observation here is the following. You see, under T duality, what? Let's see, under this flip, n goes to w and r goes to 1 by r, PL stays unchanged. But PR picks up a minus. Okay? So, we're going to try to understand T duality. This class, I'm not sure. But what we're going to try to understand, let me say the statement. That's all. What we're going to do is to imagine that we have an x, which is xi plus xi. Okay. This x split into a left moving sector, the right moving sector. T duality is the symmetry. The symmetry makes you define a new field x tilde. Okay? Which is xl minus. Okay? So the theory with field x and radius r is the same as the theory with field x tilde and radius 1 by r. That will be okay.
There's some extra issue, right? The oscillator don't change sign.
The oscillator, but oscillators don't change sign.
You also have to make some statement about what you're doing to oscillators.
Yeah, I mean, you see, the oscillator is a quadratic. The oscillator Lagrangian is quadratic. So if you take oscillator minus oscillator, nothing matters, and that's what we're doing. Okay, yeah. So this is what we're going to eventually. This will be the full claim, and this will be now a full quantum claim about every correlation. A complete equality of the conformal field theory, but we'll get there a bit slowly. Okay, sir? So that's
What happens to the oriented code business? Because here you are distinguishing left from the right.
What happens when you TDUize an orient code? We get that. It goes into something else. It goes into an order. Hang on for it. Yes. There's some interesting things happen. Yeah. But not really.
New sector related.
That's right. Hang on. Okay.
So is there any first principle reason why T-duality should be there in string theory, or it's just there?
By first principles reason, you mean what? Let's say.
Presumably people have shown that T-duality works at all, the full conformal field theory level. I mean, all the correlators, etc.
Yeah, it's very easy to say. Yeah. Because it's a free theory, it's very easy to say.
Right? So we know that it is there, but is there any much more deeper understanding as why it is there? And one could be this type 2 and type 2 coming from M theory, so you know that something has to be there which connects these things. Apart from that, just without the bridging M theory, you know anything.
No, you know, the T-duality, of course, as you know, forms a subgroup of the full duality group of string compactifications. Full duality group is called U-duality. And you know, why does string theory have such a large duality symmetry group in some fundamental ways? I don't know what it is. You know, there's probably there is. See, you can. Let's ask a simpler question. The question is, why does n equals 4 angles theory have S duality? Okay, string theory is a complicated beast, right? We don't understand all its principles. N equals 4 angles theory is a quantum field theory. We think we understand all its principles. Why does it have S duality? Okay, what? I mean, can you see from the path integral of n equals 4 angles theory, or from any way? I'm not going to stick here, but any way of fundamentally formulating n equals 4 angles theory, some way of trying to understand that it should have this duality. Because if you see it from string theory, it's clear. Because n equals 4 angles can be obtained from some other theory by torus compactification, from which is fundamentally from the properties of, you know, these questions, why certain dualities exist, I think are very poorly understood. Even in structures as well understood as field theory. You could translate that to the question of, okay, in field theory where we think we understand the formalism, can you find a formalism of field theory which makes duality manifest? I think at the moment the answer is no. Yet it's true. You know, so it's a very interesting question. I don't think. It's a good question, but I don't have anything to say. Okay, excellent. Now, before going on to a more formal presentation of this T-duality symmetry, I wanted to very quickly look at the computation of the partition function. Okay, I wanted to very quickly look at the computation of the partition function of. We'll have to stop at 10 minutes. Okay, but I have to very quickly look at the computation of the partition function in of a theory with toroidal compactification. Okay, as a warm up for this, let's actually look at the computation of the partition function of quantum mechanics, non-relativistic quantum mechanics, with Lagrangian mx dot squared by 2. When x is periodically identified. Well, so suppose I was interested in the finite. I got this theory. I think of it as a theory on. I think of it as a theory on. Yeah. Suppose I was interested in this theory. I was interested in this theory at finite temperature. At temperature beta. Can anyone tell me what the partition function is? You know the answer. At temperature 1 by beta. So I want to compute trace of e to the power minus beta. Non-relativistic quantum mechanics. One direction of space. Circle.
It's just the Bose function or something.
No, it's not both. But also,
Some of the modes.
exactly, yeah. You know the spectrum, so some of it. Maybe it is, but it's not, I mean, it's a bit.
You're on a circle, right?
Maybe a geometric series.
Not quite just zero. Let's write the answer. Almost, yeah. So majority series plus 1. Okay, yeah. And then let's go. What is the question? I'm not even quite a geometric series because it's n squared. Let's see this. What the question is with a non-reductive scalar particular on a circle. What is trace equals bar minus beta? This is a question you could be asked in your TRI. Okay, simple question. Maybe you were asked this. Okay, the answer is this: trace is simply the trace over the spectrum of the Hamilton. One way of getting the answer. The trace is simply the trace over the spectrum of the Hamilton. What is the spectrum of the Hamiltonian? Well, it's p squared by 2m squared. P we know is n squared by r squared. These are periodic. Yeah. X.
Right.
We're on a circle. What? Okay. So what do we have? We have sum over n e to the power minus beta n squared by 2m squared r squared. This is the answer, no doubt about it. Okay. Not quite a geometric series because it's n squared, but almost. Yeah, the n, by the way, runs from minus n. Now, as a warm up to what we're going to do with string theory, what I want to do is to obtain the same answer using path integrals. I got this answer using the spectrum. But I should be able to compute the same answer using path integral. How do I compute the same answer using path integral? What path integral do I need to do? Well, I need to do the Euclidean path integral with time compactified on a circle of circumference beta. Right? That's clear. Okay. So what I want to do is to do integral dx exponential of minus m x dot squared by 2 the Matsubara frequency subtracted. Okay? This path integral where x is periodic and our time is periodic. Now you see, this path integral is a sum of an infinite number of different sectors. For the same reason that we discussed before. Because this x of sigma plus 2 pi does not necessarily equal to x of sigma, but can be equal to x of sigma plus 2 pi r. Okay? So, just like we had in string theory, but now, not for canonical quantization, but for the path integral. Just in defining the path integral. What we will do is the following. We will do x is equal to sum over, let's call them w's. Wx, w. Oh, I should say that the integral runs over, the path integral is sum over w dxw. Where xw are those path integral over those fields such that as x goes to x plus. Now this is x plus beta. That's sorry, tau goes to tau plus beta. X goes to x plus 2 pi wr. Okay, so in sector w, x of tau plus beta is equal to x of tau plus 2 pi w. Is this clear? Tau is Euclidean time. Since it's Euclidean, in your mind you can think of it as a spatial direction. Is this clear? Okay? So once again, like we did in our string theory example while we did canonical quantization, but this time for the purpose of doing a path integral. Okay? Once again, what I'm going to do is to split this x function into a known function that has this funny periodicity plus something that has usual periodicity. Okay? Once again, what I do is to say x is equal to 2 pi r r w tau by beta, is that right? Beta. So tau is tau plus beta, that looks good. Okay? Plus some x tilde.
Beta is 2 pi r.
No. R is the identification of the spatial circle in X. Beta is the temperature. So we've got two different things.
We have two circles.
Yeah, we have two circles. You see, X is on a circle. And then we want to compute the partition function of this model, which is a particle on a circle at some temperature T. Two different quantities. It's very important. It's like string theory. In string theory, the sigma circle size was just 2 pi. There was one circle. And there was another size which was just 2 pi r. Here, the analog is like the sigma circle size. It's not sigma, it's a tau circle. The length, beta, not 2 pi. Is this clear? That's very important. Okay. Now, like in our previous discussion, because this guy solves the equations of motion, okay, and because, well, if you just plug it in, you'll see that this action splits up into two pieces. Quadratic in a particular solution, plus quadratic in fluctuations. The fluctuations all obey the same boundary conditions, namely normal boundary conditions. Okay? So, each of these things, the fluctuation path integral is the same. Is that clear? So what we get is sum over W times something times dx tilde e to the power minus mx tilde squared by 2. Well, this has normal boundary conditions. Okay? Now, to actually evaluate this is a bit of a pain in the neck because you have to regulate. Okay, I evaluate this path integral. This part I'm just going to borrow from what we know.
These will make a dedicated beta function and other stuff with reduced number of dimensions.
That's right. This part we've already, let me say that this part is what we do in what we've done previously. Because this was the ordinary zero mode integral, the uncompactified string. And we use some tricks. The tricks are going to the Hamilton. It doesn't matter. We use some tricks to evaluate what this was. Okay? And so that thing is just going to keep. That was the same thing. That was the thing that gave us